This is one of our continuing series of lectures on transport, convection dominated transport. In this case, we are looking at natural convection, where if you had a heated object, for example, the temperature of the fluid close to the object is higher than the ambient. Therefore, that fluid is lighter and it rises, carries along with it the heat that is from the object, and that could result in a significant enhancement of the heat transfer in practical applications. The process is called natural convection, and here the velocity field is generated from the body force exerted on the fluid due to the temperature change. We had considered the equations in the last class, the mass, momentum and energy conservation equations, and we had made a series of approximations to get simplified equations. First, in the mass conservation equation and in the inertial term in the momentum conservation equation, we assume density is a constant. That constant density is the ambient density. This approximation is valid if the change in density is small. Okay. And I said for practical applications, the thermal expansion coefficient beta is actually very small, and so even if you have changes in temperature of tens or hundreds of degrees, this change in density divided by the actual density will be numerically small. In that case, you can consider the fluid to be incompressible, and the density change can be neglected in the inertial term in the conservation equation. We also assume that the diffusivity and the viscosity are also independent of temperature. Once again, that is valid when the temperature change in absolute units is small. However, the effect of density change is included in the body force term. Okay. Those are the Boussinesq equations for natural convection. And in this case, we had scaled the equations and got the characteristic temperature scale, where L is the length scale, T naught minus T infinity is the difference in temperature between the object and the ambient, G is the acceleration due to gravity, and beta is the thermal expansion coefficient. Based on that, we had got scaled equations which depend on two dimensionless parameters, the Grashof number and the Prandtl number. As I had explained to you in the previous lecture, the Grashof number is basically the square of a Reynolds number based upon the convection velocity. Okay. The convection velocity goes as beta g delta t times L square root of. Okay. The Grashof number is the square of the Reynolds number based upon this convection velocity. Okay. That is why instead of 1 over Re that you would usually have in the conservation equations, you have 1 over Grashof number to the half. Okay. In the energy balance equation, since I have a ratio of convection and thermal diffusion, that Grashof number has to be multiplied by the Prandtl number, which is the ratio of momentum and thermal diffusion. Okay. So, I have a 1 over Gr to the half times the Prandtl number, okay, in the energy balance equation. We are looking at how to solve these equations. Okay. The first thing I had said was that the Grashof number is actually large in all practical applications. Okay. In practical applications, it goes from about 1000 to of the order of 10 power 9 or so. It is especially large because it depends upon the length scale. If I change the length scale from a centimeter to a meter, the Grashof number will increase by a factor of 10 power 6. Okay. So, it is usually large. Therefore, we can consider the case of the high Grashof number limit, just as we had considered the case of high Peclet number for natural convection heat and mass transfer. So, we had scaled the equations. Okay. In this case, we have 1 over Grashof number to the half and 1 over Prandtl number in the energy balance equation, and 1 over Grashof number to the half in both the mass and the momentum balance equations. Okay. Now, if the Grashof number is large, as it is in practical applications, if you just neglect the diffusion terms, the equations will just tell you that the temperature is a constant along streamlines. Okay. And with that, it is not able to, you cannot satisfy the boundary condition because you have neglected thermal diffusion from the surface. Therefore, you have to postulate the presence of a boundary layer near the surface whose thickness is much smaller than the characteristic length scale, such that when I scale the cross stream coordinate by that boundary layer thickness, the resulting equations are independent of Grashof number in the limit as Grashof number goes to infinity. The boundary layer thickness decreases as the Grashof number increases in such a way that the equations in terms of scaled coordinates are independent of Grashof number in the limit as Grashof number goes to infinity. Okay. So, that is the principle that we will adopt while solving this problem. So, first things first, I have to scale the cross stream coordinate by a boundary layer thickness. That boundary layer thickness depends upon angle, of course, but it does depend upon Grashof number as well. Okay. And then I put that into the conservation equations. Okay. So, let us look at the conservation equations one by one. Okay. The characteristic equation for the streamwise velocity is just equal to ux by u as usual. Okay. However, for the cross stream velocity, one has to be careful. When the boundary layer thickness is small, the cross stream velocity will be much smaller than the streamwise velocity, as we saw for the flow around a sphere. Okay. For this, we have to return to the mass conservation equation. Okay. Partial ux star by partial x star and if I rewrite this in terms of the scaled cross stream coordinate, I will get partial ux by partial x plus, note that the streamwise coordinate is still scaled by the characteristic length, because for the streamwise coordinate itself, for the streamwise coordinate along the surface, the characteristic length is the dimension of the object. The characteristic length is the dimension of the object. So, the streamwise coordinate is still scaled by the characteristic length. The cross stream coordinate is scaled by a boundary layer thickness, which is much smaller than the characteristic length. Delta is the scaled boundary layer thickness scaled by the characteristic length. Therefore, delta is much smaller than 1. The second term, I will get 1 over delta, partial u y star by partial y plus is equal to 0. Delta is a small number. Therefore, in this equation, if the contributions to the mass conservation equation from ux and uy have to be of equal magnitude, that means that uy star has to be proportional to delta itself, because ux star is the streamwise coordinate and the velocity in that direction is in fact given by the body force. In the cross stream direction, the velocity has to be 0 at the surface. Since the boundary layer thickness is small, therefore, the scaled velocity, the velocity has to decrease proportional to the boundary layer thickness, because the length scale is characteristic length scale is the boundary layer thickness, and the gradient is equal to the dimension of the velocity divided by the characteristic length scale. So, partial u by partial uy by partial y has to go as uy by delta. And if this has to be of the same magnitude as partial ux by partial x, partial ux by partial x is of order 1. That means that I have to define a velocity, a cross stream velocity scaled into delta, I am sorry, or therefore, the cross stream velocity has to be order delta smaller than the streamwise velocity. And if I define it that way, then my equation in terms of the boundary layer thickness becomes partial x okay, where y plus and uy plus are now order 1 within the modular. Okay. Put another way, okay, explained in another way, partial ux star by partial ux by partial x goes as u by L, okay, which means that partial uy by partial y has to also go as u by L for the two terms in the mass conservation equation to balance each other. Okay. However, we know that y goes as delta times L. Okay. Y goes as delta times L. Okay. It is much smaller than the characteristic dimension. That means that uy has to go as u delta. Okay. So that when I take the ratio partial uy by partial y, I will get it going as u by L. Okay. So, if the cross stream coordinate is small, the velocity in that direction will also be much smaller than the streamwise velocity. Okay. So, that is the result of scaling the mass conservation equation. Okay. So, to reiterate, or let me just write it here. Okay. The mass conservation equation becomes partial ux by partial x plus partial uy plus by partial y plus is equal to 0. Okay. I have to scale uy and y because I have rescaled the y coordinate, therefore, I have to rescale the uy coordinate as well. The velocity uy will be much smaller than the velocity ux because the distance y is much smaller than the distance in the x direction. Okay. So, that is what I get by rescaling the mass conservation equation. Now, if I look at the momentum conservation equations, okay, and I rewrite this in terms of uy plus and y plus in this case. If I rewrite these in terms of uy plus and y plus, I do not yet know what is the boundary layer thickness delta, but I will find out shortly. Okay. Now, uy plus is equal to, okay, uy star is equal to, okay, uy star is equal to delta times uy plus. Okay, I have written it the other way here. Okay. Okay. Okay, I will get delta times uy plus, okay, times partial ux star by delta partial y plus. Okay. Because uy star is delta times y plus, okay, is equal to minus partial so, the cross stream diffusion term has a coefficient 1 over delta square multiplying it, okay, and therefore, the gradients are larger in the cross stream direction. Therefore, streamwise diffusion can be neglected in comparison to cross stream diffusion. Okay. And with that, the conservation equation, okay, you can see that in the convection term, the two deltas will actually cancel out. Okay. The two deltas will actually cancel out. Okay. Okay, I should rewrite this here. Okay, y star is equal to delta y plus and uy star is equal to delta into uy plus. Okay, so, those are the conversions. Okay, y star is order delta and uy star is also order delta. Okay, So, therefore, the mass conservation equation becomes ux partial ux by partial x, okay, plus uy plus partial ux star. So, let us write the simplified equations here. Okay. That is, okay, y plus is equal to y star by delta and uy plus is equal to that is the streamwise momentum conservation equation, where I have neglected streamwise diffusion in comparison to cross stream diffusion. Let us now look at the cross stream momentum conservation equation, okay, and once again make the same substitution, y star in terms of y plus and uy star in terms of uy plus, where these uy star and y star uy plus and y plus are scaled by the boundary layer coordinate. In the y momentum conservation equation here, okay, the first term is ux star delta partial uy plus by partial x star, okay. Okay. Because uy star is delta times uy plus, okay, it is order delta, okay, plus delta uy plus into delta, okay, partial uy plus, okay, by partial y plus. I have a delta in the numerator and a delta in the denominator, okay. So, those will cancel out. I will get a minus 1 over delta partial p d star by partial y plus 1 over Grashof number to the half power, okay. I have a delta in the numerator when I write it in terms of y plus, and then I have the body force T star, okay, the acceleration due to gravity in the y direction, okay. Now, you can see that this equation reduces to delta into ux star partial uy plus once again. The largest term is the diffusion term here. Therefore, I can neglect the streamwise diffusion in comparison to the cross stream diffusion, and I have 1 over delta square in the cross stream diffusion plus a factor of delta, because uy plus is much smaller, okay, the uy velocity is much smaller. Therefore, I will get a factor of 1 over delta, and finally, I will get partial square uy plus by plus T star times G hat y. Okay. Now I can, the largest term in this case is actually this term here. Okay. The largest term in this case is the pressure gradient. I can multiply throughout by the divide throughout by the coefficient of this term, multiply throughout by delta. Okay. And I will get delta square into ux star partial uy plus by partial x star In this equation, delta is small compared to 1, the Grashof number is large compared to 1. Okay. So, therefore, in comparison to the pressure gradient, both of these terms go to 0 in the limit as delta goes to 0 or the Grashof number goes to infinity. The only term that is left behind in the y momentum equation is actually the pressure gradient. Basically tells you that the pressure has to balance, my apologies, I should have a body force term here. So, I will have a plus delta T star G y. Okay. In the limit as delta goes to 0, the body force term is small, the diffusive term 1 over Grashof number to the half, as Grashof number goes to infinity, this term is also small, inertial terms are also small, and the equation just simplifies to a condition that the pressure gradient is a constant across the boundary layer. That is not surprising. The pressure has to be balanced by the viscous, inertial and the body force terms. If the length scale is small, the pressure gradient is much larger than you would expect based upon the characteristic dimension of the object in the cross stream direction. Okay. And whereas the velocity is much smaller. So, in the leading approximation you would expect that the pressure gradient is just equal to a constant. Okay. So, this the y momentum equation just reduces to 0 is equal to minus partial of the dynamic pressure. Okay. Okay. Since the boundary layer thickness is very small, the pressure is almost a constant across it. Okay. That is all the you get from the y momentum balance equation. Okay. And finally, the temperature equation. We have to scale that as well. Temperature equation ux partial ux by partial x, okay, plus uy star was delta times uy plus, okay, into 1 over delta partial T, sorry, this should be temperature, by partial y plus is equal to 1 by Grashof number, Prandtl number, I am sorry, Grashof to the half, Prandtl number into partial square ux by partial x square plus 1 by delta square. T, this is T, it's a temperature equation. Once again in this equation, the largest term is the cross stream diffusion. In the convective terms, okay, the delta cancels out and the equation that I get is ux So, those are the simplified boundary layer equations for the temperature field. Okay. y plus is the similarity variable, the equivalent of eta that we had in the forced convection problems. In these equations, delta appears at two places. Okay. Convection and diffusion will be of equal magnitude in the limit of high Grashof number only if delta is equal to Grashof number to the minus 1 by 4. Okay. So, that delta square times Grashof number is equal to 1. Okay. So, if I choose the boundary layer thickness delta is equal to Grashof number to the minus 1/4, right, then I will get equations in which this coefficient is just equal to 1 and this coefficient is just equal to 1 over the Prandtl number, okay, expressed in this form. Okay. We have to solve these equations, of course, in order to get what is actually the correlation. However, the scaling of the correlation can be obtained quite easily. Okay. We know that the heat flux, okay, Q y, okay, will be equal to minus k partial t by partial y, okay. It's equal to minus k into t naught minus t infinity divided by L partial t star by partial y. Okay. That will be the scaling of the flux at the surface. Okay. The average flux will be an integral of this over the surface. Okay. However, the scaling of that will actually be the same. Okay. So, if I take the average flux at y is equal to 0, it will be equal to some constant. Okay. It has to be determined from these equations, okay, these scaled equations. These scaled equations contain only one parameter, that is the Prandtl number. The Grashof number has been absorbed into the boundary layer thickness. So, there is only one dimensionless number that is remaining, and that is the Prandtl number. So, the average flux can at most depend upon the Prandtl number, some constant which depends on the Prandtl number, times k t naught minus t infinity by L delta. Okay. So, it has to be that form. Okay. So, the constant we do not know yet, that constant has to be determined by actually determining the solution for the temperature field and then taking the value of this at the surface y plus is equal to 0. Okay. It gives you some constant value, we do not know that, but we know what is the scaling of the rest of the terms in the equation. Okay. And once you have that, you know that the Nusselt number is equal to the average flux divided by, okay, k into t naught minus t infinity by L. Okay. And this has to necessarily scale as some constant dependent on the Prandtl number, okay, divided by the boundary layer thickness. Scaled boundary layer thickness, but as I told you that scaled boundary layer thickness goes as Grashof number to the minus 1/4. Okay. The scaled boundary layer thickness goes as Grashof number to the minus 1/4. Therefore, the Nusselt number has to go as some constant dependent upon Prandtl number times the Grashof number to the plus 1 by 4 power. Okay. So, that is going to be the form of the correlation for natural convection in the limit of high Grashof number. That coefficient, the constant function of the Prandtl number, we do not know yet, but we know that the Nusselt number has to scale as the Grashof number to the plus 1/4 power. In the next lecture, I will briefly review this analysis once again, and I will try to give you some idea of what happens in the limits of high Prandtl number and low Prandtl number. How do these correlations appear in the limit of high Prandtl number and low Prandtl number? I will continue this in the next lecture. I will see you then.